Now, so that's one example. That's one example. Here's another example. This example is the one that's relevant to the football project. Okay? Again, if you look at players' team stat, let's say team stat. This team beats 5 teams. This team also beats 5 teams. Okay? Which team is better? You don't know. Because they both beat 5 teams. That's pretty good. What if I say this team beats the 5 teams that never wins anyway? And this team beats 5 teams that, you know, beats a lot for the team. Right? So, it's not how many times you beat your opponent. It's how many times you beat strong opponent. Right? This would be nice if we had like an arbitrary designation of who's a strong team. But let's say you don't even have that. Okay, once again, you only have records of who beats who. Okay? Now, in English football Premier League, you can say, well, this is a weak team, this is a strong team. But let's say you're coming in from a fresh perspective. You don't know anything. You just have past record. You will only be able to say, this is a strong team because it has beaten a lot of other strong teams. Right? If you are strong because you beat strong teams, that strong team is defined by being able to beat other strong teams. It becomes a recursive equation. Okay? It becomes a recursive equation. And recursive equation gets solved from eigenvector decomposition. Okay? It's mathematics. Actually, I was hoping to go into detail for the team, for the interest doing some kind of network project. There isn't one. Okay? But we can talk about that in detail. Okay? But you can imagine that you don't just beat, you don't just add how many teams you beat. It's like you don't use centrality, degree centrality. If you use degree centrality, you just count how many teams you beat. That's no good. That's no good. You want to say, if you're beating a strong team, that team is strong because it beats strong team. Because it's good. And that becomes, now, an example would be something like this. Yeah? Let's say you play video game, playing Overwatch. I don't know if you play Overwatch. Anybody plays Overwatch? Okay, there are many characters. There are many characters. Okay? Now, there's actually a relative strength matrix of Overwatch characters. Roughly speaking, you can say, if it's blue, then left column beats the row, big column. Yeah? But let's say something like, if it's blue, then this row beats the column. If this is blue, it's CCA, something like that. Red means inferior, and white means never match, even match, or never fought. Yeah? Now, something like this, it's not symmetric because A can beat B, B can also beat A, or B never beats A because they've fought many times, right? It's not always that you have two opponents beat each other and one always wins, then that's okay, right? But let's say sometimes A beats B, sometimes B beats A. Maybe you have another pair where A beats C, C never beats A, right? Or something like that. Or A never beats C, so you never know, or something like that. So you have this kind of asymmetric weighted matrix. So this is a directed weighted graph. Directed weighted graph. Yeah? This is the directed weighted graph. And these are all the characters. Yeah? Some is more like offensive, defensive, so that's characterization. Yeah, but this is sort of like offensive. So you go to PC Gamer / Overwatch Hero Counters Guide. Download this data. Yeah? So this becomes a matrix. And well, the connection is fully connected because most of the time they are connected. So this doesn't tell you who beats you, but it's a written representation. So here it would be something like Genji and 3, that's 5. I think it's some kind of scoring. Yeah, I think I put in some kind of scoring, 5, 2, 1, or whatever. And you're trying to see who's good. And you're trying to pick a player based on that. Should you be Zenyatta or McCree or Farah or I don't know, I don't care. I don't play games, by the way. I just pick this thing because it has the data. Okay? And you can do that. Oh, where's the result? I think I have the result somewhere in the algorithm. Okay? Now, the result would be choose. Yeah. The data, so just Symmetra, Zenyatta, whatever, and we analyze. So based on this, I can tell you which is the strongest character. Okay? Which is the strong. You're more than welcome to I don't know how often this matrix gets updated or whatever, right? It could be every year or something. I don't play games, I don't care. Okay? But for those of you who care, there's a relative strength for each character. You can do eigenvector centrality position and determine who is the strongest player. Okay? And this will break down between two players that maybe has the same record. Okay? And this is what you would do with the football team as well. Okay? I actually did this with the English Premier League. It's a little bit tricky because with Premier League, the population is not constant because the bottom half gets dropped. Okay? So the matrix is not constant from year to year. So that's a bit tricky. But other than that, yeah, it's applicable. It's actually the paper that I eventually published about systemic risk of banks. Okay? Basically, trying to analyze this configuration of connectivity and so forth. But well, let me go to the summary page. What we did. Now, this is highly confidential data. So I can't tell you what the banks are. Right? What I did was I put the list of 5 banks and I randomized color names. You know, yellow, green, blue, ultramarine, pink, mauve, all kind of brown, light brown, whatever. And I just make a little table. Okay? Then I throw away the list of banks. Okay? Then I use the bank, the color as designated. This is actually interconnectedness of borrowing from bank to bank. The top graph here is the size, the volume. Yeah? So based on this analysis, guys, who would you say is the most important in the network of liquidity? It would be this bank, right? Because it's tallest. Well, it turns out that due to the connectivity pattern, the emergent property is that this bank actually, this one, basically, it's not negative. This is important, but I put eigenvector centrality on the opposite scale. Okay, so this bank is actually the most important. So that's a liquidity crisis for that period of time. The central bank should put money to the central bank. Okay. So this shows you that, yeah, on the whole, you can say that banks that don't have volumes are not that important, but even banks that has the biggest volume is not the most systemically important. This is not the one that makes it great. It is important still, but not as important as this guy. Okay, it's not even as important as that guy, which is a tiny volume. But look, comes in second in terms of systemic important. So this is actually in the internet download. By the way, if you go to either ResearchNet or SSRN has some data. So if you put in my name there, you see all these tables. Well, you see a lot of other tables I go. Okay. Now, as a last example, I'm going to talk about this one. Now, this is an old. I don't know if you guys like been to high school abroad. In America, there's this thing called bar game. Bar game means it's one of those things where you run out of things to say when you're drinking. Okay? Just come up with some kind of bar game. Well, this is one of those bar games. Okay? It's saying that it's called Kevin Bacon number. Now, Kevin Bacon is an actor from the 80s, so you guys probably don't know. Anybody knows what Kevin Bacon is? No, yeah. It's one of modern day. You have to update it. Well, the point is this: the Kevin Bacon number, yeah, is the number of movies connection between actors. So instead of Kevin Bacon number, you can have whatever. I think I have to know not Dave and the other girl. Yeah. Okay, so you can have a not Dave number. Well, I'm just going to stick with Kevin Bacon. A Kevin Bacon number of 1. A Kevin Bacon number of 1 means you acted in the same movie. Okay? If you're in the same movie as Kevin Bacon, you have a Kevin Bacon number of 1. If you never acted in the same movie as Kevin Bacon, but you acted in the same movie as somebody who acts in the same movie as Kevin Bacon, you have a Kevin Bacon number of 2. Okay? And you can have a Kevin Bacon number of 3, 4, 5, 7. Okay? This is the tightness of the actor. Okay? Somebody claims no actor or actress in Hollywood has a Kevin Bacon number bigger than 6. It's like some kind of mathematical power game. It's not mathematical power game, okay? So, if you acted in the same movie as this person, who never acted in the same movie as Kevin Bacon, but acted in the same movie as this person, who did act in the same movie as Kevin Bacon, your Kevin Bacon number is 3. Yeah? Yeah? So, you can actually do this. You go to website. There's actually a website called Oracle Bacon. Yeah? OracleBacon.com. And try any now this database that they have, it's not just for Kevin Bacon. So you can put anybody. Yeah? But in this case, anybody know what Bruce Lee's Kevin Bacon number is? Well, you can go to this website and put in Bruce Lee. Yeah? Bruce Lee has a Kevin Bacon number of, on this graph, what's Bruce Lee's Kevin Bacon number? 2. Because Bruce Lee is in a movie called Marlowe, I don't know if you've seen it. That movie has Tenet Toby, I don't know who that is. Tenet Toby is in Hero at Large. I can see that movie, but that movie also has Kevin Bacon. Okay? So, Bruce Lee has a Kevin Bacon number of 2. Okay? You can do this with Thai actress or actor, doesn't matter. Okay? So that's your experimental data. By the way, before it was called Kevin Bacon number, it's called Erdos number. Because the mathematics is from the guy named Erdos. So the Erdos number is, if you publish the paper with him, you have Erdos number of 1. If you co-author paper with somebody who co-author with Erdos, you have Erdos number of 2. Okay? So originally it's called Erdos number. Hungarian mathematician. I don't know. You guys can go back and look at movies from when I was young. Do you guys know who this is? But anyway, he has a Kevin Bacon number of 1 because he's in the same movie as Kevin Bacon. Yeah, I just throw that in because most of the computer nerds knew this. This is the Tremor movie where things kind of like, this guy lives on the ground basically, and if you make vibration on the surface, it comes up with ET. It's good fun. Yeah, so this is when he came out of the ground. Yeah, so the first movie, Kevin Bacon was the hero, and I think there were 3 of them that managed to kill them all. So now here's the tricky part. When I talk about the graph, it's everybody to everybody. In this case, they're actually, pay attention to this, guys. This is important. This, you don't have one type of node. You have 2 types of nodes. One type is active. The other type is for movie. So when you count the Kevin Bacon number, you have to make 2 trips. From active to movie, from movie to active. That's 1. Okay? This mathematically is called bipartite graph. And this is also handled in the Python library network case. Yeah? So you can say that it looks like the bottom here. This is what the bipartite graph looks like. Okay? You have groups of actors lined up here and movies on the left. And to count the connectivity, you have to go 2 round trips. Yeah? Now, this example, I have to read it to you because you can't see very well. This example, for example, said Jim Carrey has a Tom Hanks number of 1 because this is Tom Hanks. Tom Hanks over here. It's in Toy Story with Jim Carrey. So Jim Carrey has a Tom Hanks number of 1. Tim Allen is also has a Tom Hanks number of 1. And then Tim Allen acts in other movies. Santa Cruz, For Richer or For Worse, Jim Carrey's in Christmas, whatever. Ernest Goes Camping. The Mask, whatnot. Tom Hanks is in other movies. Joe versus the Volcano, Bachelor, Saving Private Ryan, and League of Their Own, all kind of stuff, right? So this is just an extraction. I'm just picking 3 guys. Basically, I pick 3 guys here. And I got here. Now, obviously, this is very simple, right? It has 40 edges. So you counted the edge, the 40 edges. Now, as I increase the group, I get this. So there are actually 2 groups of actors. They're not connected yet. They're not connected. So in other words, Robin Williams and Tom Hanks are not connected yet. But if I increase more connection, they start to become more connected. So this is 231 nodes with 240 edges. You can imagine if I take a small subset, you're not connected, right? If I take a data set, eventually you become connected. In this case, there's still 2 groups that are not connected, right? This is 231 nodes, that's actors and movies, and 240 edges connection. Eventually, I think, this is the Hollywood. This is actually from outcome of the output. I downloaded the data from the internet movie actors thing. So there are 14,000 nodes. That's the total number of actors and movies, and there are 21,000 edges. Now, from this, you don't get Kevin Bacon number yet, right? But you can imagine that from here, I can extract. Now, again, there are 2 types of nodes, right? Actors and movies. I don't care about movies. I care about actors. So I go through all the counting, and I generate a list of actor parent. So that becomes actor-to-actor matrix. Once I have actor-to-actor matrix, I can do what? Probability analysis. Yeah. Now, just to make a long story short, this is really funny. The actor that is most, you can say, promiscuous, the actors who like acts with everybody. Okay? You see the movie with everybody, or she's in the movie with everybody. Well, he is the movie with a lot of actors who are in the movie with a lot of other actors. I was expecting it to be like this, kind of like smooth, right? It turns out that one actor stood out as the most promiscuous actor of all. Anybody know? Guess who that is? I should make this a homework. You can download this, download the output and find it for yourself. Yeah, but because none of you guys are working with project, right? I'm going to kind of like go skip over that. Yeah, I'll just give you the answer. Anybody wants to take a guess? Come on. It's a guy. It's a male actor. Close. Sean Connery is around here. Close. Any other guess? Roger Moore is probably not as high. Robert De Niro. Robert De Niro is everywhere. He's everywhere with everyone. Who is everywhere and everyone. So, nobody comes close. When you do an eigenvector centrality analysis of actor, Hollywood actor, Robert De Niro, by far beats everyone. I think the second one is Sean Penn. Yeah, Sean Penn is pretty good. Let me read the number. Robert De Niro, Sean Penn, Ed Harris, Gene Hackman, Anthony Hopkins, Danny DeVito, Michelle Pfeiffer. Yeah, we have the first woman, first lady, Michelle Pfeiffer. Okay, and so forth. Okay. So this is eigenvector centrality on a pairing of. Okay. So you can imagine that if you want a movie that puts a lot of actors together or something like that, chances are you can't get your agent. Maybe Robert De Niro has a very good agent or something. Yeah. But obviously, if you rank in terms of number of movies, Robert De Niro is pretty high as well, right? But maybe not as high as Ed Harris. It needs them from the connectivity. This is what we mean by emergent property, right? In particular, centrality. Okay. Now, centrality analysis. So let's look at. This is another matrix. Use inverse IDOSH. Okay, so that's it. I don't want to talk anymore today because I want to spend an hour. We have less than an hour on the student project. Okay, but this is actually. Let me share internet connection. Okay. Oops. Okay, new share. Okay, new share. Let's go to this. If you go to just Google my name, very easier. Graph PyCon. Okay, 2018. So it's on YouTube. You can look at it, and the paper is here. Graph theoretic computation in Python. Okay. Now the library itself is called NetworkX. NET NetworkX Python. There. See, NetworkX version 2.5. So go to GitHub. You can download this algorithm. Yeah. But it's not that difficult. By the way, you can do this thing online. There is this thing called online matrix calculator. I think called Bluebit or something. Plenty of things. I think one time I used this example from Bluebit. But you can do this. You can put in the matrix. Okay? You can put in the matrix and you can run something like eigenvalue decomposition. Okay? So you don't even need the library, but certainly you have to put in number. Like for example, I put 3. Oops, sorry, has to be a number. Okay, and I want to find eigenvalue. Oops. Yeah, it's in here. You can do that. Okay. So you don't have to. If you just want to do a quick analysis, you have to go to the network X. Just do eigenvectors by using online finding eigenvalue eigenvector. Okay. Oops. So let's say I put in 1, 2. Okay, let's say. Okay, fine. I don't know if this limits to just 3, but if it's limited to 3, then it's not very useful. So this side may not be that good. Now, I really would love to have time to talk about the eigenvalue decomposition. It's one of the most easy things to let's spend the rest of the class on the project. I want to talk to the no shield. Okay, so tell your friend what happened. Yeah, loud. Just come up to class. Yeah, I can't stay late after class. You guys have to be quick. Okay, loud. Come on. Recession, huh? Okay, so you are turning your attention to okay. Now this is the prelim of next class. Next class we'll talk about NLP. Okay? You guys will need this. Okay? Now you can do it in Mathematica or Python, but if it's NLP, I think Python will probably be better because you can use Google's word embedding. Now, today, in fact, I may not even need to talk about word embedding next class. You guys get it down. Okay, word. I like pizza. Okay? I like pizza. I like hamburger. I kick football. Okay? I also kick meal. Okay? Alright? These are all sentences. This is our sentences. Okay. What is a chatbot trying to do? Trying to hold a conversation. If it's trying to hold a conversation, it has to be able to take in word, right? Make some calculation, get some kind of output, turn output into word, and then speak back to you. Okay? Well, that output loop or what it does is not relevant at the moment. The point is, the first obstacle you have is input of sentences. Your input are sentences. What are you going to do? Okay. Now, this is where you come to things called natural language processing. NLP. Now, for all practical purposes, when we say NLP, we don't mean spoken. Okay? It means text, written text, okay? Type text. Okay? So you don't have to worry about character recognition yet or anything. Just assume it's done for you. The point is to have something like text. Okay? It could be in Thai, in English, it could be in any language, but it's asking, right? It's not in handwritten. Yeah? If it's handwritten, you assume you do OCR. Yeah? If it's a recording, you also assume you do voice recognition, you translate, blah blah blah. So all of this is before. Yeah? You assume that. Now, with Thai words, you have tricky situation where you don't have words. You have words in a long string of sentences, right? You have to chop them into words. Yeah. So Thai NLP is a bit more difficult because you have to do what's called chunking. Yeah. You know about this thing, right? Right? Guys, look. Right? How do you chunk the two words? If you do it by pattern search alone, you will stop here. Right? Because it is a word. You will also stop here. But if you do it with AI, so with more intelligence, you realize that together, most of the time in Thai language, you will probably be this. Okay? So you also have to do some kind of learning, machine learning. It's not just a dictionary lookup. Okay? You don't have to go from left to right, and as soon as you recognize a word, you stop. Okay? That would be too simple, and it would be error. Okay? Now this is an obvious example, but there are more subtle examples. So even chunking is difficult, but your project is English, right? Okay, so we don't have chunking. Yeah, we have words. Now, tell your friend, what do you want to do with words? Okay. So words are different, right? Words are different. What do you mean by different? It means that you look up songs from the 50s and songs from the 90s, they will have different sorts of words. Is that it? Okay. So, what do you notice about words? Are words used equally as often, one word as the next? No, right? So, and or, but these are words that will occur a lot more often, right? The word like adjacency, right? That's not going to occur a lot. So there's this thing called word frequency. Now, what I want to say is that in the old days, before machine learning, the most you can do would be frequency analysis. Okay, frequency analysis. In fact, frequency analysis was used in code breaking, primitive form of code breaking. Certain words appear a lot. So if you substitute, let's say it's wartime, you send me some ammunition. Word ammunition is going to appear a lot, like that. So either you have to say banana every time you want to say ammunition, you can kind of guess. It's kind of frequency. Okay. Now, if you're talking about word frequency alone, then the whole story is simple. You just list all the words in this dictionary, right? Let's say you have a song, database in O, and song database D, right? Right? You just join the words together, and then you just look at the frequency. Compare the word frequency. Now, if that were all you need to do, you say old song, new song, they differ by frequency. Would that be insightful enough? Probably not, right? Because the only conclusion would be saying that old songs have different words than new songs. If you want to do something more sophisticated than that, for example, if you have some kind of scoring, you want to say that there's a score of modernness, but old-fashioned. You know, this song is very old-fashioned, this song is very new, and you can predict whether or not an unknown song is old or new based on this kind of scoring. Then you have to do a lot more. So counting word frequency would not work. You have to somehow turn words into input to your machine learning output. Okay? Right? Now, let's think of how you can do it. Let's say you open up a dictionary in English. Yeah? Let's say English has 10,000 words. Or it actually has a million. Let's say it has a million words. Okay? You look at the first word, A. You say A is 1, 0. Okay? And N is equal to 0, 1, 0. And R is equal to 0, 0, 1. This is not binary. This is called one-hot encoding. One-hot encoding. Right? One-hot encoding. Okay? This one-hot encoding means that if you have a million words, you have a million representations of a million decisions. Everything 0, 1 at a time. Okay? Right? If I want to do some kind of machine learning, like if I say the word, I like what the probability to be followed by a dog or something like that, what do I have to do? I have to put in a neural network, right? Let's say. So I have to have this kind of where this thing is is 1 million vector long, right? It's a million vector of 0 and 1. Okay? And then this is the neural network. Now, anybody sees a problem with that? What do we do? It's very hard to, well, the dimension is too big, right? Right? So somehow you want to reduce the dimension. So this goes back to lecture 4 or 5 when we talk about unsupervised learning. Okay? We'll talk about it in detail next class, but you remember two things, right, about dimensionality reduction. You have something that lives in big dimension. You can imagine, right? You have X and Y that lives in 500 dimension. You want to map X into X prime, Y prime in 2 dimensions. So you can plot them in scatter plot, right? Now, what is the requirement? What is the requirement? The requirement is that if X and Y are far apart in 500 dimensions, they have to be far apart in 2 dimensions. If they are close in 500 dimensions, they have to be close in 2 dimensions, right? So you do this. This is called dimensionality reduction, right? And I think we use PCA as an example. Okay? So you get something like this. Points that are close together and points that are far apart. Right? Now, the dimension is arbitrary. It's kind of artificial dimension. There's no axis, y-axis. But you can say 2 points are close together or far apart. All right? Now, what else did I say? I said sometimes it's not, the objective is not to plot into 2 dimension scatter plot. Sometimes you start with 500,000 dimensions. You want to reduce it to a manageable 300, so that the 300 can be used as input to the neural network. That is also called dimensionality reduction. Okay? Dimensionality reduction in this case reduced from huge dimension down to manageable. Now manageable could be hundreds. You still don't plot it, but it's still manageable. Now what's that got to do with our problem? You have a dictionary of 1 million words. You have to reduce the representation of words into lower dimensions. Right? Something like 300 is good number. So this dimensionality reduction is what you have to do first. Okay? What it means is that instead of having 1 million words, each word represented by a vector of 1 million zeros and one, okay, with a unique one for one part encoding, you have vector of real number of 300. The trick is words that are close together in the dictionary have to be close together in a reduced dimension. That seems like an obvious thing, right? That seems like an obvious thing. Yeah? Words that are close together will be close together in the 300 dimension. Anybody else sees that you can do something better? Well, words are not closer just only in the dictionary. They're also closer in context. So when I say, I don't like being bitten by an ant, another word for ant that would make perfect sense is, I don't like to be bitten by a bee. Right? But I would never say something like, I don't like to be bitten by art. So ant and art are very closer by spelling, right? Ant and art is close by spelling. But in context, they're not close. Okay? I'm going to a picnic, but it's a bad day for picnic because this park has lots of ants. Okay, you can say that. I don't like to go to picnic to this park because this park has lots of bees, has lots of wasps, has a lot of hornets. Right? You never say, I don't like to go to this park because you know, we can't go picnic there because this park has a lot of arts. Right? So arts and ants are close in spelling, but they're not close in context. Right? They're not close in context. The key is that somehow I want to reduce word representation that's close together, not in the 300, in the million dimension, but close in terms of context. So that ants and wasps and hornets and bees will be closer together than art. Okay? You see that? So this kind of context preserving dimensionality reduction is what you need in order to prepare your data set. Okay? And next class, I'll talk a little bit more in depth about how this is done in real life. And that's under the concept of word feedback. Word feedback. Okay? So I reduce bees into some vector and ants to some vector such that they are closer together than between ant and art. Even though spelling is very close. Yeah? So this is called, the technique is called word to vector. Literally, word to the letter to vector. Word to vector. Okay? But the whole approach is called embedding. Embedding word to vector into vector. Okay? A word embedding. And that's what we're going to learn for next class. That's going to be relevant for the Erno Shield. Okay, how about other team? Who's running into trouble? Yeah, we have 15 minutes. Quick. Yeah, go. Yes, please. Now stop sharing. You can use eigenvector centrality analysis as well. But I think you've got quite a lot already. Your project has a lot to play with already, so that's good. Okay, go. Nếuกดแชร์ Okay, let's zoom หน่อยลูก
So, we have to use Python in manipulating the data and create some data graph.
Data graph, yeah.
So at first we think that we divide each attributes by like for shooting, right? There will only the scores will only become for players in attacking and midfield positions, and for defending will only become score for goalkeeper and attack.
Okay. Now you're still working from the 6th dimension for players and 6th dimension for goalies, right?
But
okay, no goalies. So you have 6 for offensive player and 6 for defense or midfield. And everybody.
We make it together because the first time that we did it, we tried to separate it, right? And we saw that the graph for each team would be very similar as well.
Or I think it will be the same because they're trying to go to
Mm-hmm.
For for each.
Oh, okay, okay. So now you're adding everybody, but you can't add the goalie, right? Because the season.
So when we add everybody, the information also taken into consideration.
Okay.
Because if the team got more defenders,
Fine, fine.
so we did some experiment, and for like yesterday, last night I did this like the attributes. So you can see that it's very close to each other. And that's what's on the right.
Good, fine.
And next,
This is anomalies on radar chart. And we have the attribute from the
So the team with the rate chart, like the overall is rating is higher than the target chart.
Good, it should be like that.
But the outcome is
different.
Yeah, this is good. No, because if the team with better players in every aspect wins, that's what two-time economists do. This is good, this is good, this is good, this is good. You got two of this, you got two of that. But this case, you might say something like, okay, just make a narrative. It could be something like physicality. The game was very physical, so that the precision of passing, dribbling didn't matter. It's just kind of like tackling each other. Okay, that's what Brazilian accuse English players of doing anyway. So if you do this with maybe Brazilian team, you say something like, oh, you know, they're better everywhere, but the team was so physical that you know, you get overrun. Yeah, so the team that has more physical. But again, this is not that sharp, right? It's not that clear. But based on this, you could almost make a story. Now, machine learning is not about making a story. It's about evidence, building you the story. So if this was all the graph you have, you only have one chart, the whole history of football. You can say that the team with physicality wins. That's it, because you have a database, data sample of one. Now, you can learn from this using machine learning. Learn who, you know, combination. So maybe it's not the whole football. Okay? So what may happen? What may happen is this. If teams have better players overall, then you have more likely winners. But the exception, you can say, well, out of 10 exceptions, what were the distinguishing features? It may be physicality, it may be passing skill, it may be team chemistry, I don't know. Okay, you can do that. So the result is not confirming to what you believe, that's fine, that's not wrong. That's good, that's insight, okay? ถ้ามันกำปั้นทุบดินไม่ต้องทำ
This is also looking at the everything that has to do with
Yeah. So what was the bottom? I can't see it. Dribbling. Right. So it's something like this. Now, you have to be very careful though that insight like this can make for a very interesting post-game analysis. Okay? You can literally show this graph on ESPN and appear like an expert. But if you want to really do data science, it has to be statistically meaningful, right? So you have to run the example, run the model, and you can say that, yeah, whenever this thing breaks out, it tends to highly predict. Okay? So it's about predictability. Okay? It's about predictability of system and
but the problem we're running into that for each we should like very hard for our team. When facing with the player, I cannot do that lineup.
yeah, that's fine.
And when we're going to that, like the training,
That's precisely where you need machine learning. Because if you can say, I'm just focusing on Liverpool, And it would be nice if Liverpool put the same set of players all the time. You don't need machine learning, right? You just make a table of say when do they beat, when do they lose, right? It's precisely because these have different combinations that you can't do like traditional statistics. Okay, traditional statistics would work if Liverpool fields the same set of 11 players, Madrid always the same set of 11 players, and they play each other 30 times a season. You can do statistics, right? You don't need machine learning. It's precisely because your inputs are not constant, right? That's why you need machine learning. So you would put input where in this data set, right? Sometimes Liverpool will put this combination of player with that combination of player from the other team, and this is the result, right? It's not orthogonal. In other words, because this is not a design experiment, you can't say, okay, last night Liverpool put this set of player and Madrid, and Liverpool lost. What if Liverpool put different set of player and Madrid put the same set of player? Who would win? You can't do that experiment, right? That's the whole point. See, you can't figure all the combination, all things being different by add more forward, add less defensive. That's experimental design that you can do in your lab. Okay? Machine learning learns from real data, and real data. You know, you said, you know, you go to Liverpool and say, you know, I can build you a very good model. But in order for me to do that, you have to try all the configuration. It's going to be silly because it doesn't care, right? So it may be that for this season, this set of players that they field is 11 players. And this combination works so well, they use it for 90% of the time. And they ask you, what if I use other combination? And you say, well, for me to answer that, you have to try the next 5 games with this combination. That's silly, right? You can't make them do that, right? You have to learn from real data. So this is not a problem at all. That's precisely where machine learning comes in. The issue is you have to design your validation or testing set so that you say, if I learn from this set of data, does it predict well? Okay, you can't second guess a computer. All right, you're doing, you know, you're doing something that you shouldn't do. And by the way, you would make the worst manager. And I run into that a lot when I build a machine learning algorithm and say send it to management, and they try to scrutinize because they use two-thumb method. Say, hey, how come this data point has this? Why not that? You know, and ask me to explain how the neural network works or something like that. That'd be the worst. You can't second guess. Okay? You can't say beforehand that, yeah, because it dominates, it has to win. If it doesn't win, it's because of this. But the data can be contradictory. That's the whole point. Okay? You can't manhandle the data. You can't specifically okay? You can't go say, in this case, it has to be like this because of that. Because I believe that is precisely the wrong kind of interference. And by the way, that's real life. Manager will interfere with your model precisely in that manner. They have intuition of what variable should translate to what. And if it doesn't go according to their intuition, they say, I don't understand. And if you say this is the result of the machine learning, they say, oh, machine learning is a black box because you can't explain it. Well, real life is a black box. You can't always explain why this combination of players is that combination of players. That's why you have on paper surprise. On paper, this looks like a stronger team, put together the lose. Okay? But experientially, over time, the machine will pick up the pattern. Okay? So machine learning doesn't tell you why. And if you're trying to say it has to work this way because I think this is how it works, this is why things work, this is why work team A, B, D because of this factor. You can't do that. Okay? You have to trust that you design your machine learning experiment so well that it tests predictability. Okay? That's a very bad way of getting lost. Okay? But your experiment has to work on a control testing validation. You're on the right track. I think you're on the right track. No, I wouldn't. I would just, you doing things on the aggregate anyway. You aggregating all the players. So why not all the matches? Yeah. Yes. Because every single match has a roster of players. Okay. Now forget substitution. That's a little bit tricky. Okay. Just say starting player. Okay. Starting player roster. Right. The first 11 means 11. Okay. You add the attribute. So you add 6 number 11 times. Add 6 number 11 times. Have this cobweb compete with that cobweb and the result. That's one data point. One match, one data point. Forget Liverpool. That's too few. They can only play how many games a season? Yeah, then you train the new one. What the way I show you, right? Yeah. Mathematics is much easier. You want to ask me. You can prepare all the data in Python, and then just get the data is only like math, right? You have what? How many matches do you have? How many matches? What? Nothing. All right? Nothing. All right? Yeah, that's where you can ask Peanut for. That's the Python piece. Data munching. That's what it's good for. Your database has to contain who's playing. Yeah. You have that. All right? Okay. Suicide. How are you doing? Okay. This one must talk. Go. Guys, pay attention to your friend. Okay, one. Yeah. Facebook, picture, like, response. Okay. Yeah, good. Fine. Yeah. Okay, yeah. A priori algorithm usually used for data mining, this kind of counting. Now, I don't know, because you do have. Okay, but a priori, that's not perform supervised learning, right? From what I understand, it doesn't do that for you. Okay, so you can do association. So they try to do this thing. They try to do this association of objects in the picture with association of lights and dislights. Okay, that's probably doable. Good. Come on. Which one? Detectors. Okay, that's the spectral analysis team, right? Okay. Okay. ต้อง stop share หรือคือไม่ได้ stop
นี่ครับนี่เล็กเชอร์ที่อาจารย์พูดนะครับผมนั่งไว้นี่ไหนอ๋อมีน้องอยู่จะทยอยขึ้นแต่ว่า
ใครที่มาสายชื่อพี่นัทนะฮะมีแต่เฉพาะคนที่มาทำเวลา
วันที่เราอาจารย์ตอนที่บอกความจริงใช่ไหมอาจารย์บอกให้เราทำผิดแล้วผมเลยอาจารย์จะเล่นตัวเล็กผมเลยต้องเล่นดูเล็กชื่อให้ตัดต่อซะนะเดี๋ยวจะให้อาจารย์
Yeah, fine. I suspect that this is a much easier problem than last time. Because remember last time we talked about convolutional filter, right? Even if you didn't do the trend filter, there's some kind of filter built in. You just run through here. Yeah. I would imagine this is a lot easier than the spectral. Yeah. Yeah, with the saturated, correct? Yeah. Now, this would be digital image processing in the age where you actually have a filter in mind. I want to detect vertical. I want to detect horizontal. Okay? Now again, with things like convolutional neural network, you generalize it to say, just detect any kind of pattern. Okay? So I would imagine that not pre-specifying the convolutional filter would be a better approach. You see what I mean? So let's say, I'm vertical again. Just maybe just pass through a convolutional neural network, and it's going to learn because the ground truth is given. The hard part of machine learning is not that ground truth. The easy part is the algorithm. Yeah, you can use trivial CNN architecture. Scan through, yes, no, etc. Yeah, and it's actually going to end up with a convolutional filter that is more fine-tuned. And when you say X detector, it's going to be generic. It's like when you look at Wikipedia, and they write, this is a convolutional filter, detecting vertical, detecting horizontal, it's pretty generic. Now, if you use a neural network, you need convolutional rating. Good. Yeah. Good. Yeah, binarize. can also do color reverse, so that sometimes it's black with a white track, or white with a black track. Sometimes you might want to play around with that. Color negate, I think it's called. So once you get to this, then your image becomes black and white, right? So you can rasterize to a fixed dimension like 28 by 28 and use the net. Do that, right? Again, in this case, it will be Lynette architecture without the weight, right? Because you're not learning numbers now, you're learning computation. And you don't want to divide. Basically, you probably take a lot of one. Okay, that's a crap. So it'll be like linear crap. Good. That's very good. Yeah, yeah. Yes. Yeah. Cluster analysis is always useful. The way I work, even though I end up with supervised learning engine, in the beginning, I would go like this, okay? The data looks at it's clean, nice. Visualization, unsupervised learning, supervised learning. That tends to be the general flow. Unsupervised learning gives you the insight. Rising export, then format. Okay, I actually have to be somewhere, so okay, one more. Bravo. IMDb data set. Okay, just the two of you. Yeah, speak loud. Share. Good.
Create a picture graph to analyze. And I try to create a model to find a factor that differs the data analysis between two time periods of the data set. Like in this time period, this genre is very popular, like after the pandemic.
Yeah, it should be something like that.
And then pandemic happened, nobody wants to follow anymore. That's like the animation.
Okay, you guys hear that? They want to do the genre distribution. Yeah, they want to do like a genre breakdown. You know, like maybe before 9/11, people were more interested in romantic comedies or something like that. My own, and then afterward, maybe they're looking for more action, whatever movies. My only suggestion would be that don't start with a supervised learning approach first. By supervised learning approach, you mean you have to decide on a cutoff line. Say, this is before 9/11, this is after 9/11. What happened before, what happened after? Now, with unsupervised learning, you can do kind of like a pattern shift over time, okay? It may well be that, let me give you an example. 9/11, let me give you an example. 9/11 changes the composition of movie genre, let's say, okay? But if you were doing it as a supervised learning, you have to say 9/11 happens in 2011, and let's say the cutoff date is 2012. Imagine that the shift in genre takes effect in 2013. You will not detect the pattern because you arbitrarily chose the graph before 2012 and after 2012. But if you do unsupervised learning, you do a clustering year by year, it would tell you literally without any prompting that there's a big shift in 2013. You can relate 2013 to 9/11. right? So be careful about immediately jumping to supervised learning formulation, because that's assuming you can create a ground truth. I don't think you can. Okay, see what I mean? So if you do a movie composition year by year, you can maybe detect a sharp change, maybe 2014. Okay, then you can do further analysis. Is it a function of 2000, 9/11 post-production date? Okay, but I would caution against jumping to supervised learning right away. Try to organize the data to that first. Visualization. Okay, histogram of genre, year by year. Okay, something like that. That would be my suggestion. Good, but you're on your way. You're on your way, and you have no problem with data, so that's good. So as long as you have no problem with data, methodology, I can help you. Okay, no problem at all whatsoever. Okay, again, whoever came late, check in with Inat. So, okay, I have to be somewhere, so next week. สวัสดีครับ สวัสดีครับ